Hello everyone, and welcome back to the Fluctus Channel. Behind the striking power of an aircraft carrier lies one of the greatest engineering challenges in naval warfare: how to launch a high-performance warplane from a runway far shorter than one on land. A carrier's flight deck simply does not offer enough distance for a heavy jet to accelerate on its own, which forced the US Navy to invent systems capable of throwing aircraft to takeoff speed in only seconds. Early carriers relied on hydraulic catapults. But after the Second World War, those systems were replaced by steam catapults, which used pressurized steam to drive a piston and shuttle along a launch track. That breakthrough transformed carrier aviation, allowing heavier and more capable aircraft to operate from ships at sea. Over time, supercarriers such as the Nimitz class were fitted with as many as 4 catapults, enabling rapid launch cycles and turning the carrier into a true floating airbase. Although launch procedures vary slightly depending on the carrier and its technology, the process itself follows a disciplined sequence. Aircraft are taxied into position at the rear of the launch track, where deck crews guide the pilot into exact alignment. The jet is then connected at the nose gear to the catapult shuttle and restrained at the rear by a holdback device, which prevents movement until the catapult reaches full force. Around the aircraft, multiple teams work at once. Jet blast deflectors rise behind the aircraft to shield nearby personnel and equipment from engine exhaust. On steam-powered carriers, boilers deep inside the ship generate high-pressure steam that is directed into the catapult cylinders. When the required pressure is reached and all safety checks are complete, the system is triggered. The shuttle surges forward, dragging the aircraft with it and accelerating it from a standstill to flying speed in just a few seconds. It is one of the most violent but precisely controlled actions in military aviation. Even though steam catapults served reliably for decades, the Navy has developed a newer launch method aimed at improving efficiency, reducing maintenance, and delivering smoother acceleration. That system is EMALS, the Electromagnetic Aircraft Launch System. Instead of relying on steam pressure, EMALS uses a linear induction motor to generate the force needed to move the launch carriage. Along a track of about 300 feet, energized stator coils create a magnetic field that drives the shuttle forward. To do this, the system draws huge amounts of energy from onboard generators, stores that energy kinetically in large rotating alternators spinning at about 6,400 RPM, and then releases it through a power conversion subsystem at the correct voltage and frequency. This allows the aircraft to accelerate in a more controlled way than with steam. One of EMALS's biggest advantages is smoother acceleration, which reduces stress on aircraft structures during launch. It also requires fewer maintenance cycles and can launch a wider range of naval aircraft, making it a major step forward in carrier aviation technology. Its path to operational use, however, was long and technically demanding. General Atomics received the contract to build EMALS in the late 1990s, but turning the concept into a working carrier system took years of development and testing. In 2004, the Navy began evaluating the technology, but full-scale land-based trials accelerated only in the 2010s. During that period, carrier aircraft such as the C-2 Greyhound were used in tests on long runways to verify aircraft compatibility and system safety. These trials were essential because engineers needed to prove not only that the system worked, but that it could launch real aircraft without causing unacceptable stress or danger. From those land-based sessions, EMALS moved to sea with its installation aboard USS Gerald R. Ford, CVN-78. Testing there began with no-load launches, followed by dead-load shots using wheeled steel test vehicles weighing up to 80,000 pounds to simulate different aircraft weights. These tests demonstrated the structural integrity of the catapult and allowed the Navy to refine the system before expanding into live aviation operations. By 2021, EMALS had progressed through full ship shock trials and aircraft compatibility tests involving Super Hornets, Hawkeyes, and Growlers. The results were strong enough to support future installations on carriers such as USS John F. Kennedy and USS Enterprise. What started as an experimental replacement for steam was becoming the next standard in U.S. carrier aviation. But the catapult itself is only one part of a much larger launch network. Safe and efficient carrier operations depend on several systems and teams working together in exact coordination. At the center of the process is the integrated catapult control system, often associated with the bubble, a hemispherical control station that rises from the flight deck. This station houses the catapult officers, or shooters, along with operators responsible for overseeing launches. Inside are the consoles, indicators, and monitoring systems used to track each phase of catapult operation. Because the bubble offers a clear view of the flight deck, the crew inside can monitor aircraft alignment, deck crew positioning, and final safety checks. During inactive periods, the structure can retract into the deck to protect it from weather and seawater exposure. When launch operations begin with aircraft, such as the F-35, the officers inside the bubble coordinate directly with the flight deck crew to confirm that the aircraft is properly positioned, attached to the catapult, and restrained by the holdback system. The integrated catapult control system also communicates with the ship's navigation bridge to verify that wind, weather, and deck conditions are safe for launch. At the same time, launch officers confirm that the catapult is fully ready, checking hydraulic status, steam pressure, or voltage levels in the case of EMALS. Only once every element is confirmed do they signal the pilot that launch is imminent. Then, in an instant, the catapult is released, and the aircraft is accelerated down the deck and into the sky. The same emphasis on coordination continues during recovery operations because landing on a carrier can be just as difficult as launching from one. Modern carriers use systems such as the Advanced Arresting Gear, or AAG. Unlike older arresting systems, AAG uses energy-absorbing water turbines connected to an induction motor, allowing better control of the arresting forces that stop an aircraft after touchdown. Alongside AAG, the Navy has introduced technologies like the Joint Precision Approach and Landing System, or JPALS. JPALS uses real-time GPS-based guidance to help pilots approach the carrier more accurately, even in poor visibility or at night. Tests aboard USS Abraham Lincoln with F-35C aircraft showed that the system could guide aircraft with near 1-meter accuracy, offering a major improvement in landing precision. Even with the arrival of steam catapults, EMALS, and advanced landing systems, not every Navy has followed the same path. Because catapult systems are expensive, mechanically complex, and demanding in energy and maintenance, many countries adopted a simpler alternative: the ski jump. This upward curved ramp at the bow of the carrier allows an aircraft to leave the deck at an upward angle, giving it a positive climb rate even though the runway is short. In these cases, the aircraft relies entirely on its own engines to reach takeoff speed. This method is generally most effective for jets specifically designed or adapted for short takeoff or vertical landing operations, such as the F-35B or the British Sea Harrier. All of these technologies, steam catapults, EMALS, arresting gear, JPALS, and ski jumps, exist because aircraft carriers are full of limitations. Their runways are short, their decks move with the sea, and their operations demand extreme precision under difficult conditions. Yet those limits have driven some of the most creative and powerful engineering solutions in modern warfare. From the thunder of steam launches to the smooth magnetic pull of EMALS, the systems invented to launch feared warplanes from carriers show how necessity can produce extraordinary technology. And every time a fighter is hurled from the deck into the sky, it is not just an aircraft taking off, it is decades of naval innovation in motion. And after all the engineering behind catapults, launch bars, arresting gear, and landing systems, the flight deck still depends on something much simpler to keep chaos under control: color. On a U.S. aircraft carrier, the deck is divided by jersey colors, each one marking a different job in the middle of one of the most dangerous working environments in the world. Green shirts are typically assigned to catapult and arresting gear crews, aircraft maintenance, and certain technical support roles, the people who help keep launching and recovery systems working. Purple shirts, often called grapes, handle aviation fuel, making sure every aircraft is serviced safely before flight. Red shirts work with ordnance and explosive handling, loading bombs and missiles onto aircraft during combat operations. Blue shirts are the aircraft handlers and chalk and chain crews who help move, secure, and position jets across the deck. Yellow shirts are the directors, the highly visible deck controllers, who guide aircraft with hand signals and visual authority through the noise and danger of carrier operations. One of the most critical figures in this entire system is the Landing Signal Officer, or LSO. During recovery, the LSO watches incoming aircraft closely, monitors glide path and lineup, and can order a wave-off if a landing becomes unsafe. That role becomes especially important because landing on a moving ship with a short-angled deck leaves almost no room for error. Together with the flight deck crews, LSOs are part of the final layer of control that turns a violent, high-speed carrier recovery into a repeatable naval procedure. So, in the end, the carrier deck is more than just steel, steam, and electromagnetic force. It is a tightly choreographed battlefield where technology and people have to function as one. From the catapult below the deck, to the shooter in the bubble, to the yellow shirt on the flight line and the LSO watching the landing, every part of the system exists for one purpose: to launch feared warplanes safely and bring them home again. That's the end of this video. I hope you enjoyed it. Make sure to subscribe to this channel so you don't miss any of our new content. See you next time.